Recording in progress.
Cool. That should be working. It is phenomenal. Right. Okay, let's go ahead and get started today. Assuming projectors are going to start. Oh, there we go. Great. Okay, so starting as per the usual with some announcements. There's going to be another practice quiz today, as there is every Friday, or we don't have an actual quiz. We're also going to have a Monday in-class discussion on the future of game AI topics. As a reminder, in case you've forgotten, because we only covered it like at the very beginning when I was covering the syllabus, the way that this is going to work is that the last sort of 3 or 4 lectures, you all are going to get to pick the topics on, which also means that you get to pick the topics for the last quiz. So on Friday, or on Monday rather, we'll talk about some students have suggested. At the end of the practice quiz, I'm going to ask for your ideas before I start biasing you with prior suggestions. All right. Also on Monday, I'll release a helper video for assignment 3 for those of you who are waiting on it. You'll note that it's not going to be as structured as the last 2 assignment videos because there's not pseudocode to follow in these cases. It's going to be some sort of suggestions, but it's not going to be as much like participants can now see my screen. Could they not before? Doesn't matter. It's more going to be sort of high level sort of suggestions and things like that. We'll have a lab next Thursday, which is going to be a helper session for assignment 3 because it's going to be due, 3 days after that lab session. Right now, I guess it's going to be in person. We'll see. Who knows? Tomorrow we could be like, ta-da, we're all going online for a while again. Quiz 3 is going to be next Friday as well. Okay, any questions? Oh yeah, and then of course assignment 3 is due October 25th. Any questions on any of this? Okay, cool. All right, so a quick review on decision making because it's been a bit since we last actually talked about decision making. In fact, it's been a week. So the basic idea for game AI decision making is it's how the AI is going to pick what action it's going to actually be doing next, right? Now we've talked about 3 different techniques so far. Those were finite state machines, behavior trees, and rule systems. These 2 were on quiz 2, which means that this one is going to be on quiz 3, behavior trees, in case, for those of you who couldn't see me pointing. Finite state machines look like this, right? There's a small confusion here because finite state machine talks about enemy actions in terms of states. We also have a notion of the game state. There's 2 different notions of state. In both cases, right, we're going to look at one entity and sort of freeze it in time and space. But whether that's the whole environment or whether it's a single entity, that's the distinction. So, right, we have a set of states. We're going to transition between the states. We can only be in one state at once. Behavior trees, slightly different, right? We're going to go from a root node down to whatever our final action we're going to be taking is. And then finally, rule systems. Basically, we're going to see what all rules could fire, and then we're going to select from there what actually fires. Basic distinction. Now, there's a few problems with this current sort of set of approaches. What is shallowness? So what I mean by shallowness is that the behaviors that they can exhibit are pretty limited, right? There's no notion of sort of large complex behaviors unless the human had to go down and sort of pre-author them, right? And our ability to respond is really limited to what's happening right now. So none of these approaches have the ability to say, think ahead, to say what's coming up and then plan around that or react to that, right? You're based on what's now. There's also adaptability. This is related, but it's a distinct point, right? So we can only do explicitly what the human authored us to be able to do as a game AI agent, and that's it. And that works in situations where we want to have like strict control. It's not always what we want. Finally, related to the above 2 points, right? If both of these are about human authoring, then of course it has a heavy design burden. Humans have to do a lot of authoring to be able to actually use these approaches. So a quick reminder on rules, and it'll become clear why we have to do a reminder on rules in just a second. So each rule has 2 parts. There's a condition, which can be thought of as like the if statement, if this is true, right? And then there's the effect, then do this, the change that you want to make in the world, right? And we talked about how a rule is only activated if all of its conditions are met. And basically it says it can but doesn't have to be used. This is the case a couple of you had issues with for quiz 2 of thinking that, oh, just had to have some of its conditions met, right? Or the most of its conditions met. No, it has to be all of its conditions met for the rule side of things. So, right, examples could be things like, all right, let's have an unlock door rule. And the unlock door rule says, if we have a key, then if the door is locked, we're going to set that door lock to false. Or shoot an enemy. If we have a gun and ammo and we can ray cast to the enemy, then we're going to subtract our gun's damage from the enemy, right? So this is the basic structure for how rules work. Now, just a second ago, I said we had this problem with shallowness, right? That we can only do things right based on one thing. We can only respond to one thing, what's happening now. What if we could chain multiple rules together, right? So in situations like this, right, if we have an unlock door and shoot enemy rule, and if we're in a situation where an enemy is hidden behind a door and we have a key, but we need to actually go get the enemy, right? That's the whole goal. Then we could chain multiple actions together into a sequence, which we would call a plan. Now, plan is a word when we're talking about path planning. But in this case, we're talking about planning in the action space. So we're back talking about planning in terms of MCTS style planning. But with MCTS, we were doing this like weird approximation that's not necessary all the time. So this is planning, right? High level idea is that we want to give each agent a goal or a set of goals. We're gonna have conditions to reach to stop planning. Basically, that's what the goal statement is. It could be things like kill the player, make money, etc. We also want to give the agent access to a pool of actions with cause and effects. Those are the rules. And finally, we're going to have a sequence of actions to reach said goal. That's the plan. So plans show up all the time, or we can think about plans showing up all the time in basically anything you're doing in your day-to-day life. So for example, route search, right? This is basically all of the path planning lectures. How do you get from here to there? Anytime you all are having to go to a new building on campus, right? You're basically doing path planning. You're going, okay, well, I know how to get to here, then here, then here. Ta-da, we're there, right? Of course, people used to have to do this with driving, but then Google Maps showed up. Things like military options can be thought of as plans. Outlining a new coding project could be thought of as plans. How are you going to approach that? Coming up with dance choreography, composing a piece of music, writing a script, etc. Basically anything that requires forethought, that requires you to think about it ahead of time and come up with some sequence of actions you're going to do to achieve it, that can be represented as a plan. So a plan is a very ubiquitous approach, just in CS and in AI broadly, not just for game AI. Okay, let's look at an example. And by look at an example, I mean I'm going to have you do an example. This is going to be a PQ in a second. Before you're getting out your phones, I want to actually talk you through this sort of environment to make sure you understand what's going on. So the goal is up in the top right. The goal is that we want to have the key in our inventory. In this case, the key is that little boss key with the horns on it, or we've also got link up in the top. And we have a little gauntlet over here. So let's say we have the following rules. We can pick up an item if we're at the same location as the item, then we can add the item to our inventory. We can move, so if we, if it's open, if a particular spot is open, and that spot is a neighbor of the player's position to that location, right? This is just movement, this is just grid movement. And then finally push. So if inventory has the gauntlet, that's this thing you write over here, and we're neighbors to the boulder, then we can move the boulder away from the player. Okay? Cool. Everybody understand this sort of breakdown, the problem setup. Some nods, I appreciate the nods. Okay, with that, let's start the first PQ. So I want you to give me the plan, which is going to be a sequence of rules to fire to reach the goal. You can just describe it if it would be a lot of like, and then you do this action a lot, for example. Just as an example, who knows why that would be a thing that I'd say. But yeah. /goes dash. Alrighty. Quick set this to. Oh, hello. Oh, okay, there we go. This is fine. Is there a way that I can? Yes. All right, keep that up. Sorry, it's going to be blank for just a second. Or a little bit longer than a second. There we go. All right. And of course, my video froze because it has to freeze every single time. Okay. All right. Sorry, let's bring that back up. Nice if I could set it up. We're going to have like one projector on one screen, another projector on another screen. I don't know if that's possible. I assume the people got this, but just in case you haven't, throw that in there. All righty. We got two people. Let's see what these first two people said. Oh, we got a number of them. So some people gave me the parameters. Some people didn't give me the parameters, it looks like. So the issue here with this one, for example, here, I'm just going to copy. Ooh, I was going to copy and paste it. Nope. Hello. Hello. So the issue with like this one, for example, I'll put this up here. Throw you over there. Go ahead and throw this on screen. So the problem with, let me make that actually legible. The problem with this plan, for example, is that it completely ignores the preconditions, right? So it says we're going to pick up the gauntlet. We're which we can't do because we're not next to the gauntlet, or the gauntlet for that matter. And then we want to move towards the boulder and then move the boulder past the canal. It's a canal, it's fun. And then retrieve the key. So the move actions are really important here in terms of setting up the preconditions necessary to actually do those actions, right? So this would not be a valid plan. Let's see, let's jump back over here. We do have a number of valid plans, right? This is a valid plan, picking up, then moving, then pushing, then moving, then moving, then picking up. This sort of description, I like this description. But you don't need to go into this much detail. Yeah, a whole bunch of you have got the basic idea, right? We need to move to the gauntlet, pick up the gauntlet, move to the boulder, push the boulder, move to the key, pick up the key. If you're missing any part of those, then it wouldn't be a fully valid plan. Okay. Wow, it's having a hard time going back to full screen every time I do it. Okay, anyway, here's my answer, right? So as you can, oh, a chat message. What's up, chat? We'd have to move the boulder from the bottom rather than from the left, though, right? Yeah, so technically, Maricel is pointing out that the way that the rule was written, if we were at this position right here and we push, then the boulder would end up over the key. So Maricel is correct. We'd actually want to be pushing it from here or from up here to be able to avoid pushing it into the key. That's correct. But anyway, so we'd want to move, right, pick up, move, push, move, 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 and pick up. Right? Everybody basically, most people basically got that. Oh, hello. So how do we define a planning problem? You just did a planning problem, right? But you're not an AI, at least don't think you are. And we need to actually set this up in a way that we can have an AI solve this as opposed to a human, who it's pretty easy to recognize global sort of needs like that. This is also very funny. Literally this morning, I was watching a keynote from Graham Ritter at the AID conference that I've been attending this week, which is literally on planning, in this case for automatic place testing. So the three sort of parts that we have here are the rules, which we've already talked about, right? This is basically what can we do in the world as the AI agent. Then we have our environment, domain, or state representation. This is just three different ways of saying the same thing, which is how do we represent the world and what can exist within it. And then finally, some goal, right? What are we trying to achieve? This is really necessary because we can't just take actions at random, right? And we have to have some way of knowing how are we getting closer or further away from that goal. So if we have these three things, we next need to figure out how we can start to plan. A very simple approach, in fact, the approach that was used in the keynote that I was just watching this morning is called forward planning or chaining. It's also referred to as strips, and this comes from way back in 1971. This is right, this is 2 AI winters ago. For those of you who know that term. Basic idea is that given some current state, we want to pick out our activated rules, the things we can do, right? We want to then check each potential activated rule, which will generate a potential neighboring state, right? This is a whole world, a whole different world, right? We're thinking about parallel realities here. And we want to pick the next current state from our set of neighbors, according to some heuristic. And then finally, when we hit a goal, we want to backtrack to some construct or sequence of actions necessary to achieve the goal. This should sound pretty familiar. What does this sound like? Anybody? It's an algorithm you've already seen. A-star. Yeah, this is literally A-star, right? Forward planning, when you're using this sort of world space, you can use things like A-star or greedy to sort of do forward planning. I'll give you an example of this problem, right? But for example, we might have something like this initial state over here on the left, where we have A's on the table, C's on top of A on the table, B on the top of B and the top of C are both clear, and our goal is to get to A, B, C sort of stacked up in this way. This is called like a block world problem. It's one of the earliest planning sort of problems from back in the 1970s. Imagining how would a robot solve this problem. And right, you obviously, because you're humans, can very easily go, well, obviously you move C and then B and then A, right? But to an AI, trying to figure out what actions you do is a little trickier. And that's why we have this notion of like parallel sort of realities, imagining other worlds, right? So each one of these nodes in this case is a whole representation of the world state, a whole representation of our domain or environment, right? We can think about how we move through this world state to get from where we start to where we want to end up. Does that make sense? Now, we don't have this representation, right? This is a visualization of the ways that we can move through this world state, but the AI doesn't have it. It's just like with pathing planning. We can only see where we are and locally around ourselves. So we figuring out how do we get to where we want to go just using this local information. And sometimes local information is deceptive, right? So as a reminder, right, this was just A star again. The only distinction here is that these neighbors here represent the activated actions firing, the activated rules firing to get our neighboring world states. We're not just looking at movement anymore. So it can be movement, as you saw in the sort of Link example, the Zelda example that I gave a second ago. Okay, so let's talk about this and solve this problem, given this current state, given these rules, and given this goal. So first of all, from our initial state, we can look at what are the things we can do from here. We have 3 actions we can do, right? We can move to our left, we can move down, we can move to our right. And that's represented here, left, down, and right. From there, we would sort of like continue this process iteratively. Now, there's gonna be a lot of branching here, right? Because we're gonna be looking at a lot of things that are just not necessary. If we're looking at this specifically in terms of like the heuristic that we've been talking about so far, the sort of distance to the goal, that's sort of the heuristics as a reminder that we've been talking about when we're talking about path planning, then this state actually looks the best of these 3, right? Because this one, we're very far away from the goal, and this one, we're almost as far away from the goal, even though it's technically the better of the 3 states. So how do we actually get it to tell it, no, this is bad and this is good, right? How do we fix this problem? Well, a common way to do this is to actually change our goal representation. So instead of saying we just location, now our goal represents the entire state that we want to get to, right? We want the boulder to be away from us, right? We want the key to be gone, and we want to be where the key was. This state is actually impossible because I should have put the boulder on the other side. We'll ignore that for now. Actually, no, it's not impossible. Never mind. Ignore that I said that. Ignore times 2. Then basically what we can do is we can write a heuristic. Instead of the heuristic being the distance from our current position to our goal position, the distance changes between our current state and the goal state that we're trying to get to. Does that make sense? This is change in the way that we've been talking about changes like the number of edits that you would need to make sure you're not replicating my answer on a quiz, for example, right? We're talking about edit distance here. I'm not going to talk through this because you all can read, and I think you have the basic idea. But the essential notion here, is that we'd be looking at, why does this keep happening? Okay, there we go. We'd be looking at a heuristic with a max value of 4 in terms of the number of differences we care about, where each check could be either 0 or 1. So for here now, our heuristic looks very different. If we're still using A star, all of these actually look equally good because we haven't made any progress, right? But at least we have the situation where we're not going to get stuck in a corner for a while. So maybe that's still not the best. So what if we did something slightly different? So for example, what if we search from the goal backwards to get a plan? We know where we want to end up. Could we, instead of going forwards through our current state to our goal, go from our goal to our current state? This is a little bit trickier. This is called backwards planning or chaining. And it can, in some situations, cut down on search time. And it can allow for more general goal specification. So instead of having to say, we want the player to be in this exact location, we want the key to be gone, et cetera, instead we can just say like, oh, I shouldn't have clicked again, sorry. Instead we can just say, here's the things that have to be true in the world for this state to be a goal. So if we want to go from our goal state back to our initial state, we're basically going to use our rules in reverse. So we're going to say, okay, we know the effects already. What would have to be true for this rule to have fired, for these conditions of this rule to have been true? We then want to pick the rule whose effects fulfill the conditions, right, the most. And we can use the same sorts of heuristics in terms of picking between them if there's equally good ones. Right, so in this case, we might have a goal that was like inventory has the key. That's it. That's our only goal, right? That's the goal that I gave you initially. We could then say, okay, well, if we're going to pick up the key, then we'd have to be in the same location as the key. So we immediately know where Link has to be, where this funny little guy has to be. But what we don't know, which is why it's represented by question marks, is where the boulder would be in this state and where the gauntlet would be in this state. Those are 2 things that we wouldn't know because we're sort of inventing this state as we go along. So then we could go backwards from there, right? So we could say, okay, well, to be able to get there, what we would have to do? Well, we would have to have moved there, right? Because we weren't there initially, we would have to have moved there. And then immediately we get into this problem, right? Where you can see to be able to have moved back again, we would have to have moved through the boulder. So prior to doing that, we must have pushed the boulder, right? And then you can sort of reason backwards like that. Cool? Okay, so forward planning. Pros, it's intuitive. This is the way that most people tend to think about sort of planning type problems, think about thinking ahead. It's also a natural fit to typical graph search approaches because it's just path planning again, right? It's just path planning, but we have actions now. It can also handle inconsistent actions. This is really important. So there's going to be some situations where we have random things with actions. We have like a random effect, right? If this is a game of some sort, maybe it's like an RPG battler or something like that, right? You can have a random amount of damage that you do. And so with a forward planning, we can deal with that because we can forward simulate and say, okay, well, in this rollout, we would have gotten this random action, but if we instead gotten this random effect, we would have done this and this and this and this, right? You can sort of branch out based on handling inconsistency. But backwards planning can't do that. There's also some cons though. So there's going to be irrelevant actions. So this is the thing I showed you earlier where we had like 3 sort of movements that all looked equally good, right? Because in no cases were we actually doing anything with the items in the world. So therefore, we're going to have sort of high branching factors. So we're going to have lots of children for each node, which is going to slow us down. Backwards planning, on the other hand, is only going to consider necessary actions, right? Strictly necessary actions. But the cons is that it is susceptible to long backtracks when effects negate decisions, right? So if we could have had something where for the boulder, we could have like pushed the boulder back and forth, and we could have pushed or pulled the boulder, right? We could have gone back and forth, pushing and pulling the boulder infinitely, which wouldn't have been great. And it also works poorly with inconsistent actions, right? Because we have no way of knowing, hey, which of the effects had to have fired, which of the things had to have worked. The random effects had to have happened such that we got to where we got. Okay, so none of these approaches, forwards or backwards planning, is really used in games. Now, I know I said a second ago that they were used for automated playtesting, but that was during the development process. There's a reason why none of these approaches are actually used in games. Is anybody familiar with Bethesda's notion of Radiant AI? Yeah, I'm far too old. That's fine. So I'm going to click this button. We are not going to listen to the audio. So you're not going to hear Todd Howard's dulcet tones. But instead, I will narrate because audio in this room, as we've learned, is a nightmare. So let's see. How do I do this? Oh, I literally can't. Oh, give me a second. There we go. Cool. It's taking a long time every day to do this. That's weird. Okay, so let's take a look here. Whoa, slow zoom. All right. So this is a video, as you can see right there, right? It's an E3 2005 demo video, so a long, long time ago. But this was, is anybody familiar with Oblivion, which is a game before Skyrim? Okay, there's some hands, appreciate the hands. So this was right after the success that Bethesda, oh, that's quality. Let's see if we can slightly increase the quality, huh? Auto is oh my God, the best is 360p. Oh, I'm so sorry. It's gonna look like a motion blur nightmare. What can you do? You know, this was 2005. We just didn't have the pixels back then. Anyway, this is right after the success of Bethesda with their game Morrowind. And they really wanted to do things that were interesting for their new game that was about to come out, Oblivion, which is sort of this like classic fantasy game, if you couldn't already tell by the very blurry architecture, right? So that one of the big things they wanted was to have AI characters, that lady just said something, AI characters that actually sort of seemed like they were real humans, that they had lives that they lived. So they would have characters that would wander around on like fixed patrols, that would have activities that get into gossip conversations. They had this whole notion here. They're saying like, oh, did you hear about Kvatch? Kvatch got truly messed up by some demons. And the idea is that you were then going to get like a new topic in a conversation that you talk to other people about. Now they dropped this mostly because people found it frustrating to have to sit around waiting for terrible AI voice acting. You can't hear the voice acting, but it's about as quality as what I just did. Also, yeah, those animations, huh? Yeah, so now you can talk about the Daedra attack because you overheard them talking about the Daedra attack. Daedra is their fancy word for demons. Anyway, let's jump forward a little bit. Okay, so at this point, you're going to talk to this lady. And the idea here, wow, that's dark. There's nothing I can do. It's just going to look terrifying and demonic. The idea is here, you've just wandered into this lady's house. And what they were trying to do with this demo is sort of show off that this lady has goals of her own and she will do things to try to achieve those goals, right? This is just planning. So rather than having to specify all their things that their AI could do, I'm going to jump forward again. They instead could just have them give them general goals and then let them try to achieve those goals. So at this point, she's going upstairs. You can't see because it looks like just dark mess. But now she's upstairs. That was her, the sort of shadowy figure. And Todd Howard is talking about how the characters in the game have goals and relationships. So she has this dog that you can't quite see, very low poly dog. What she's going to do now is she wants to practice archery because she has a goal to be better at archery. So just like the player, if AI characters practice a thing, they would improve their skills in it in the original build. So this is her practicing archery. She's cursing in like a funny way. We're all supposed to be laughing. She's not very good. Now it's going to show her that she's going to go to her sort of nightstand over here. She's going to pick up a potion. The potion is going to make her better at archery, just like it was player. So that was a goal thing, right? I'm like, okay, I want to be better at archery. What's a simple way to be better at archery? I'm going to take this potion and then I'm going to be better at archery, right? I'm going to be more consistently hitting the target than she was before. Now this dog over here is going to start like barking and yapping in just a second because the dog also is a goal-based planner. And what its thing is it doesn't want to be hungry. Typical dog behavior. And so it's yapping and yapping and yapping. And so she's going to feed it. So she's feeding it now. Again, you can't quite see because of how dark it is in the room. People who are watching online will be able to see a lot better. But the dog is still yapping because now has lots of energy, which is just a thing they decided happens when you eat. She's now trying to read because she also wants to get better at reading, I guess. But really it's just a setup for this moment. Where she kills her dog because it was making too much noise. A lot of dogs die in this class. I don't know why. It's not my doing. Anyway, so this was like a funny example they put together for E3, but it was actually a broader problem. So they had an issue, right? If all of your AI agents are planning all the time, right? What this means is you're using all the rules, right? The basic actions that the player can use in these games. And the basic actions that the player can use in these games is to do violence, right? Is to kill things. So that means that if the NPCs had goals and they had these actions where most of these actions were kill things, most of what they do is kill things. And so players during playtesting would show up to towns that were entirely empty because all the NPCs went on like a murder rampage and killed one another. And like maybe that would work in like a post-apocalyptic sort of nightmare game, but like wasn't the vibe they were going for here. So they way scaled back the Radiant AI feature. They went back to behavior trees. They were like, okay, this is going to be a lot more controllable, right? They still kept some things like this notion of like fixed schedules and stuff like that, but they way scaled back because they didn't want the ability to yeah, unfortunately. Again, you can watch this later. Sorry, people in the chat. But again, yeah, they didn't want it to have this much controllability, or sorry, this much freedom. So here's the basic question, right? If we can't just do forward planning or backwards chaining because we need to ensure that whatever plan we end up with, whatever behavior we end up with matches a designer vision, AKA if you are just a villager in a fantasy town, you shouldn't murder everyone, right? How can we enforce that? Well, instead of having to search through states and constructing a plan, we can instead search through possible plans. This is a bit of a different idea, but just as like how before we were searching through world states as opposed to locations, instead we're going to search through possible plans as opposed to world states. And then, right, we can use a heuristic to sort of ensure that the plan that we get actually matches our designer requirements. So the idea here, or one of the approaches for this is called partial order planning, or POP, which is nice that it has that acronym. We're going to basically use the same structure for the path planning approaches before, but we're going to add what are called ordering constraints to action. So some actions must occur before or after others. There's a few distinct pieces of vocab for this. So there's a notion of a conflict. So a conflict says action C conflicts with some partial plan A to B. So basically C says, or rather, if we do C, then it's going to conflict with what we've already set up when we're doing this plan going from A to B. So if A has, right, so like, a door is unlocked, for example, and B has a precondition P, like a door is unlocked, and C has an effect, not P, like I'm going to lock the door, for example, then C cannot, or sorry, and if C can occur between A and B, or otherwise I should say, then in this case, we call this a conflict, right? Because C is introducing a conflict. C would make it no longer possible to go from A to B, right? Okay, appreciate the nods. Sorry, I'm kind of zooming today, but we have a lot to go through in a practice quiz. I will do an additional review of planning on Monday because we're also going to keep talking about planning on Monday, but some more advanced approaches. Anyway, a consistent plan then is one with no cycles, right? Because we can't have a cycle where we'd have the NPC behavior just sort of stuck doing the same thing over and over again. And no conflicts, right? Which would make a plan invalid. Then one last thing, we have a notion of a solution, right? Which is a consistent plan with no open preconditions, which is to say everything is satisfied, everything can happen, the whole plan is valid. Okay, so the POP algorithm works a little bit like this. We want to start with some initial plan, which is start, finish. So we have our start state and our end state, and that's it. Where start can be in order before finish. Obviously, there's a conflict, right? Or rather, this is an inconsistent plan because there's open preconditions. We can't just go from start to finish. This should be like saying that we could go from that initial state with link in the top left corner to the state where link just has the key, right? We can't just jump right there. So we're going to pick one flaw, which is some open precondition on conflict, like, for example, the fact that link isn't in the same location as the key. Then we want to arbitrarily, we can arbitrarily pick this, or we can do it based on some heuristic to say guide it towards picking certain kinds of flaws. We then want to generate what's called a successor plan. This is like our notion of a neighborhood, right? When we're talking about traditional planning, which is every possible consistent way that we could resolve that one flaw. And then we want to pick these plans based on some, pick from these plans based on some heuristic. So if link had the possibility instead to kill somebody to get the key, and we didn't want to have link killing people, then we would say, okay, reject that way, reject that plan, instead pick a different plan. Finally, we want to iterate through this and then stop when the solution is reached. So let's look at an example, because I think this is going to be most helpful to look at for an example. So let's say that you are an AI agent, you have two goals in life. You want to kill a possum that has been tormenting you, and you want to be rich. Two things. We all want, of course. And then we have these set of actions. So we can buy a gun. We can always buy a gun. So if nothing, then buy gun. Or sorry, if nothing, then has gun, because we'll have bought the gun. We want to buy ammo, which also has no preconditions. If blank, then has ammo. We need to load the gun. So if we have a gun and we have ammo and the gun isn't loaded, we can load the gun and we don't have ammo anymore because it's in the gun. Then we want to rob a bank. This is a thing we can do. So if loaded gun and has gun, then we're rich. Isn't that amazing? And then finally, shoot possum. So if we have a loaded gun and there's not a dead possum, the dead possum becomes true and we no longer have a loaded gun because we shot it. So it's a single use gun in this case. All right, everybody got the rules? So in terms of ordering constraints, you have to buy the gun before you can load it, right? You have to buy ammo before you can load the gun. And you have to load the gun before you can shoot the possum. And you have to load the gun before you rob the bank. So these are our 4 ordering constraints. These are just built in. These are given by the author of the system. We then start with an empty plan, as I just said, right? Where we just have the start and the goal state in it. Our start state is we're not rich and the possum's not dead. What a shame. And we are rich and the possum is dead in our goal state. This plan has 2 flaws, right? Which is we're not rich and the possum's not dead, as I said. So let's say we pick one, like is rich. So if we want to pick is rich, right? Then we know that the only way we have to get rich in this world is to rob a bank. Okay. So if that's true, then we hook up this action to this precondition. This is referred to as a causal link, which is the link that effects of an action to the precondition they satisfy. If there were any other actions or ways to become rich in this world, then we could also have alternative ways of doing this, but there's not because it's a simple example. Sort of cartoon logic, right? Of course, I should have just said they born rich, obviously. So then we also Another flaw, right, which in this case is we don't have a loaded gun. In this world, I guess they can tell when you don't have a loaded gun, you try to rob a bank. But anyway, so we want to load our gun to be able to have a loaded gun, right? So one way of doing that. Then we pick another flaw. In this case, possum dead, which is shoot possum. Now you'll note here, we don't have a notion of the ordering between these two yet. Eventually, we'll need to be in just one ordering because we can only do one thing at a time. But right now, we have just a notion of they're sort of like floating ambiguously in space. So to be able to shoot the possum, or sorry, for the possum to be dead, we need to shoot the possum. But this introduces a conflict, right? Because to shoot the possum, we'll no longer have a loaded gun, right? But to be able to rob the bank, we need to have a loaded gun. So this is the exact situation I gave before, right? With this being A, B, and C. Okay, is that clear? So pretty simple, right? To resolve the conflict, all we have to do is say, well, you have to go ahead and rob the bank first before you shoot the possum. Even though none of the preconditions or effects match up here, just because of the fact that this conflict has been introduced, this tells us the order in which we need to do these things. Does that make sense? Okay, if you're interested, here's the giant pseudocode for partial order planning. We're not going to go through it because we don't have the time and because you're not going to need to know it. As long as you have the high level idea of how to do partial order planning, that's all you're going to need for the quiz. But if you're interested, it's there. Okay, so in terms of heuristics, we can do things like having a domain independent heuristic, which would be like the number of flaws in the plan or the length of the plan, because we prefer shorter plans to be more optimal. Domain dependent heuristics would be like the designer intent, like, hey, actually, you shouldn't rob banks, right? Or kill dogs. Now, benefits of plannings are things like agents can make decisions, exhibit behaviors that were not pre-authored. So it's all the benefits of rule-based systems, but instead of the problem of rule-based systems, which is you were super local, right? The plans can actually have fairly complicated behavior, fairly complex, fairly intelligent-looking behavior. It also reduces authoring burden, right? You still have to author all the initial rules, but then you don't have to author all the ways they can be hooked up together, right? The sort of equivalent here is, right, imagine an FSM or a B tree where you just have to do the action nodes and not the linkages between them. That's sort of what's going on. It also then, of course, increases flexibility of the AI agents. Now, problems, right? It takes a long time to actually make a plan, especially if our plans are super like high level. Designers are also going to surrender complete control, right? This is the problem with Bethesda. They weren't happy with having murderous, psychopathic NPCs, and so they got rid of it. It's also difficult to debug, right? For pretty clear reasons, right? It has all the problems of rule-based systems plus extra complexity. So in terms of applications, right? There are cases where I was like literally watching this morning, just one example, there's others, of using this for play testing, the basic idea of like sending your agent as a planner through the environment like it was the player to try to find bugs. This can be very powerful. This is also where you can use reinforcement learning. We'll get to that later. And then there's also particular like indie applications like Elsinore for particular kinds of game AI. If you're not familiar with it, Elsinore, the basic idea is that you're playing as Ophelia and Hamlet, but you can change how Hamlet would go. And then the AI agents are going to try to plan around you to still try to do Hamlet. So it's your goal to try to sort of get them away from Hamlet, away from that like death spiral of Shakespeare's. Now on Monday, we're going to cover the one asterisk example of AAAI of using planning in games, which is in the Fear series, or rather in Fear 2005. Interesting how that was like the same year. What's going on there? We'll get to that later. Now it's not exactly true, right? It was also used in the Killzone series, and actually recently in Square Enix's Left Alive, which is this like mech tactics game. But it's still like, I can give you exactly like 3 times it was used ever in AAA games, as opposed to like FSMs and B trees, and even rule-based systems, where I could be like, okay, here's 3 examples in the last year or so of where these were used. Okay, with that, it is quiz time. There's a little bit less time than I wanted for the quiz, but we're just going to jump right into it. I'll leave this up for just a second, and then I will also put this in here, but it is pretty darn straightforward in terms of the URL for this. It is just tinyurl.com/guz-quiz3 to represent this is the 3rd practice quiz. And with that, I'll give you about 7-ish minutes, and then we'll really quickly go over the quiz. Oh, did I muck that up again? Sean has pointed out that I didn't actually not collecting emails. I can change that. I have the power. Oh, that's not it. Here we go. Too many windows. Collect emails, limit to one response. All right, that should be fixed. Apologies. Got it for the first PQ today, not the second one though. Who's done? Nobody. All right. Take another few minutes. Okay, apologies if you're not done, but I want to really quickly go over this. Also, we'll probably go over time, so if you need to like jump out, feel free to do so. So first one, which of the following requires at least runtime computation? Who thinks it's A, planning, Definitely not that. We talked about it today, right? Who thinks it's B, FSMs? All right, one hand, I like it. Who thinks it's C, B trees? And who thinks it is D, rule systems? No, it's FSMs, right? We talked about this, right? FSMs are only going to have to check the state they're currently in, and they don't have to do any extra checks, or they have to look at the state transitions from that state, and that's it. B trees have to go all the way down the tree, right? Every single time. And rule systems have to check every single rule that could potentially fire. Thank you for getting the FSM. So 2, imagine a path planning approach with the following rules. I'm not going to read them, but the basic idea is that we need the goal to be 6, C is equal to 6, but we want to have a heuristic that prefers smaller plans the most variety. So we could just run rule 1 6 times, right? Assuming that C is equal to 0 to start. But that wouldn't give us the most variety. So we actually want to use a set of 1, 2, and 3. There's several correct answers here. It depends on which heuristic is I would actually give you, which have to be a little bit more specific. 3, what planning approach would you use to generate this plan? Forward planning would work just fine for this. So I'd recommend using just like forward planning or partial order planning. Back chaining is not as necessary for something like this because it's just, you can just, forward simulate very easily. And then finally, this can be whatever you want, right? The idea is that I'm just going to get some ideas from you here, and then I'll give my own sort of suggestions on Monday, and then collectively we'll figure out what we want to do after that. Okay, cool. I think that's it. Thank you all. I'll hang out here for a few minutes. Weren't even at over time, which is great. I'll hang out here for a few minutes if there's any questions, and then otherwise on Monday we'll continue talking about planning, and specifically hierarchical task networks. Whew. All right. Any questions on Zoom? Does not seem like it. Go ahead.